Okay, let's start by motivations. So the ranking-based propositions has become part of everyday life. It is now commonplace to choose movies, travels, or clothes after seeing certain tips. Ranking is typically adopted by companies in high-risk domains such as creditworthiness or hiring. And this paper is focused on a post-processing approach to ensure a final fair rank considering multiple protected attributes. So in general, the goal of a ranking is to associate to each item DI a score YI to create a permutation of P Greek of all the elements in D. By J uguale P Greek I, we denote the item in D at rank J, where J goes from 1 to n. So a better position in the rank denotes a better utility of the item for the user. Next point, we must verify that this rank P Greek is fair in respect of groups G. The fair rank problem is necessary whenever P Greek is unfair. So the goal is to calculate a new rank omega such that should fairly represent all protected groups G and preserve as much as utility as possible from the original rank P Greek. So on the right, we can see graphs about colorblind ranking, where the items or individuals are ordered by decreasing order of score YI, and a fair ranking on the bottom, which fairly represents all protected groups G. Okay. So, but how we measure utility or fairness? For our concern utility, in our paper, we're working of multinomial fair algorithm, take into account drop of utility in respect of the original rank P Greek, remaining into fairness boundaries. So, by the literature, we use some metrics like individual exposure that take into account for each individual the rank position, express as 1 over natural logarithm of 2 plus J, where J is the position in the ranking. Discounted cumulative gain, that is the score YI discounted by exposure, and Kendall tau, that we can think about Kendall tau as a similarity metric between the original rank P Greek and the new rank omega. So Kendall tau is a statistical measure typically used to confront similarity between distributions. But how to measure fairness? We have various ways. We can calculate average exposure across groups to compare them. We have a disparate treatment ratio that it can be calculated with a measure of utility like discounted cumulative gain over average exposure. And then we have statistical tests run over the cumulative distribution function for a binomial distribution, which is we are calculating if this new rank fits this distribution to ensure if given minimum proportions expressed as P are respected. So the starting algorithm was developed by Zelig, and it is useful to create a new rank, calculating position by position while using an hypothesis test to check if new rank fits binomial distribution. This latter establishes if the distribution fits given proportion parameters for each group. So multinomial fair select iteratively individuals with high score that belong to low exposure protected groups to fit them to given proportion passed to binomial distribution. Selected individuals are positioned in a better rank J in new ranking domain. It selects which individuals D to put in J, simulating the adding of this latter and calculating the value of binomial distribution for each protected group. And it selects the individual that guarantee the better value of fairness in terms of alpha C. However, this approach does not guarantee the maximum utility in terms of similarity with the original rank and discounted cumulative gain. In fact, it's possible that a solution that do not guarantee maximum utility for position J is equally fair, but with a better utility. Problem. I lost the presentation. Okay. So, paper contribution lays in the fact that the multinomial FAIR is extended in order to allow the user to choose which metric to maximize, if fairness or utility. They were fixed with the original algorithm, multinomial FAIR. Users so can act in choosing the preferred configuration referred to fairness or utility. You can act on the trade-off working on L parameter that can vary between 0 and 1, where L is equal to 0. When L is equal to 0, there's the preservation of fairness obtaining multinomial FAIR algorithm. While L is equal to 1, it maximizes utility, remaining into fairness boundaries. Experiments are conducted to demonstrate the efficacy and flexibility of our approach. In particular, we have demonstrated that we can find better solution in respect of those founded by a multinomial FAIR, respecting fairness boundaries. So the experiments are on the benchmark dataset adult, and so we have these plots that shows original rank P Greek with colorblind ranking and multinomial FAIR when the algorithm is run and adapt the distribution to respect fairness constraints. So we suppose that we want to maximize utility as expressed in terms of Kendall tau. Under this assumption, our research questions are: could there be solutions that maximize Kendall tau that satisfy the fairness boundaries that are not covered by multinomial? In other terms, can the value of L that maximizes Kendall tau be different from 1 or 0? Could there be solutions that maximize Kendall tau that satisfy the fairness boundaries that are not covered by multinomial FAIR? In other terms, can the value of L that maximizes Kendall tau be different from 1 or 0? So the experimental evidence suggests that the relationship between Kendall tau and L is not linear, and the maximum utility is found between 0 and 1. So it confirmed the significance of our approach. Results are consistent with for different values of alpha. So we propose a method that builds upon multinomial FAIR, providing as a contribution the flexibility to choose the preferred trade-off between fairness and utility. Our approach allows for identified FAIR optimal solutions in terms of utility metrics other than DCG. And we illustrated that when L is between 0 and 1, with configurations not covered by multinomial FAIR, it is possible to obtain better utility values while still meeting the fairness constraints. So optimal configurations are not consistent among all utility metrics. Therefore, the user sensitivity in choosing the most appropriate metric for his context remains crucial. Thank you.